So now I'll start talking about some data analysis. We have two kind of labs that we need to talk about for our data analysis. We have both the elimination and the addition lab. So where we're going to start is with the elimination, because the elimination, like we had already kind of addressed, was a lot more quantitative and forces some kind of comparisons. So to do that data analysis, what you should be looking at is the elimination group data document. Okay? There are some hiccups within that group data analysis. So if you guys remember from the lab, you produced very, very tiny amounts of product. Okay? Those tiny amounts of product sort of worked with the IR or worked fairly well with the base preparation, but were pretty awful as far as the acid preparation went. Okay? That was not your fault at all that anybody can prove, so we'll just say it wasn't your fault. But it is something that we kind of have to watch out for and think about. Because you produce such small amounts of product, we could not collect NMR data on every individual's experiment. And so instead what happened is we pooled, and by we, I mean I, pooled the acid product that I had and pooled the base product that I had into separate NMR and then ran those spectra. Kind of, sort of? Okay. So those spectra then, because there's really only two, I decided to not put into individual pre-labs. So nobody has an NMR spectra in your pre-lab or your notebook. Where they are located is in the shared document. So theoretically within this document, every group went in and uploaded their IR and pertinent lab observations. There weren't a whole lot of pertinent lab observations to put in, but you could have put some in. Okay, so you've got the IR, and then in a couple cases, I believe this first group is actually an NMR. It was one of the first samples, and I decided to run it, and we have this as NMR data. So we could go through and use this. If we look at this spectrum, I want you to note a couple things. First and foremost, I should have zoomed in on the screen. We have 1 ppm there. We're looking at 5 here. And what we're looking at officially is a bit stupid. We're looking at a camera picture of the screen for the record. I know that's dumb, but I'm an idiot and I've not figured out how to get the spectra off of the stupid instrument and onto the computer to make it look nicer. So, tough. I can't screenshot off the instrument either. It's not a true computer. Yeah. The only way I'm aware of is you have to have a flash drive. How many people are carrying a flash drive? Yeah, that's what I thought. Okay. I had to go home and ask my wife to pull out the flash drive. She's like, I don't know where they are, but here's this giant vase, and in the giant vase we had like 20 flash drives, all covered, thickly covered with dust, debris, and grossness. And so I had to pull some random ones out and test them to figure out to get them how to work. In any case, side story. That's how we'd have to get it off. Even if we got the NMR spectra off, the next problem is it's in a file that is only interpretable by certain software. That software costs thousands of dollars. Okay, so you don't have a way of doing it either. So all the interpretation has to happen on the instrument, which leaves you kind of out of the picture and leaves it to me. So within this spectra that we're looking at, a couple things I want to point out. Number one, you can see that the spectrum is entirely cut off. Okay? So what happened here is that part of the spectrum decided that we could ignore. We'll talk about why in a second. And we zoomed in right here to evaluate this. This is really setting us up with two signals. We'll call one about 5.2 and the other one about 4.7. 4 looks like that. Okay? Those two signals become important, and we'll talk about why in a little bit once we address them. Okay? But that was the point of the zoom in, was to see those. If we continue to kind of scroll through lectures, ooh, wow, dang, someone provided a lot of context. Okay, we can see our IR spectra. They're showing the same, really, they're showing the same one. That seems a bit sus, but whatever. Okay, nope, so maybe that was No, that's not. I don't know why that same one is showing up multiple times, but it is what it is. This spectrum, if you look, looks a little bit different, right? Why does this one look different? Or how does this one look different? Might be a better question. Okay. Here we're seeing these kind of smooth lines to these peaks, whereas up here we've got all these jagged lines. Why? It actually has nothing to do with the purity of the sample. It has to do with how much. So those jagged lines are because there's very tiny amounts of the product actually in the NMR tube to be tested, which means what the instrument is seeing is hardly anything to pick up a signal. Okay? That signal is now the bump upwards. It's so noisy that that's why you're seeing all those jagged lines. That becomes very difficult to go through and interpret because of where it's located. Okay, so if we go through and increase the concentration, now we reduce the noise and it allows us to get a better peak. So when we're looking at analyzing the spectra, this is the spectra that you should be looking at for the alcohol. Okay, so the alcohol was, sorry for the scrolling, the acid preparation. Okay, and that's going to become important. We'll talk through that in a little bit when we actually get into the data analysis. So that's our acid preparation. Okay, if we continue to scroll through, in theory we move to the base preparation, we see some IR, and we would go through and see the NMR for the base. Okay, the IR, the crappy NMR that we saw for the acid was because I only ran one acid NMR. The base, I waited until I had enough pooled to actually run the NMR, okay, which is why this one looks a little bit cleaner. You'll note that we see the same two peaks. We see about 5.25 and about 4.7. Okay, I'm actually going to pull these out. Did I already pull them out? No, I didn't. Because we're going to want to look at these in a little bit. So this was base. Oops, wrong one. And then our acid one was here. Come on, thank you. Okay. So what are we supposed to do with this? Well, that's where the post-lab comes into play, and the post-lab tries to break it down into a couple different steps. We got to keep scrolling until we get to the very end. Apologize. And we could look at literature spectra of what we would expect to see. So first and foremost, we could go through and look at the IR of what the IR was supposed to look like. So you can look at the literature IR and compare it to the IR of your possible or what your products were and see how they align. If we compare these two IR, this one, this bottom one is for the 2-butene, and the top one is for what I'm calling what I will call the 1-butene. So 1-but and 2-but. Okay, and if we compare those two IR, what do you see? Okay, you might say, oh, it's shifted to the left, but we got to be aware of the frame of reference. This set of peaks is at 3,000, that set of peaks is at 3,000. Said another way, do you see much difference? You see a lot of difference?
Well, in the fingerprint range, but that's pretty much it.
Okay, so going into the fingerprint range, maybe we could see much of a difference.
It's kind of flat.
Okay, and then we potentially run into problems. When we talked through this lab, we said there were two possible answers. We could form the 1-butene or the 2-butene, or both. And if I have both, are you going to be able to interpret the fingerprint very well? No. So what you're going to try to do as best as possible with the IR is compare your IR to these literature and see how they align. Okay. Ideally, other groups have also put in their IR, so you can check to see, is your IR consistent with other groups' IRs that ran that experiment? Does that make sense? Okay? And you could try to make those comparisons and draw conclusions. It's not going to be great with the IR because what does IR show you?
Just bonds.
Just bonds. And are the bonds different?
No.
No, not really. Okay, so if we're looking at the 1-butene, and we'll keep coming back to these structures, that's our 1-butene, whoops, that's our 1-butene, and then our 2-butene was that structure. Okay, so there's not a whole lot of difference between those, which means the IR is probably not going to be useful. So that's where we would hope that the NMR would show us some difference. Should the NMR show us any difference? Yeah, it should. Okay, what we should look at would be the hydrogens connected to the pi bond. Those are going to be the most unique. The 1-butene has those 2 hydrogens connected to the pi bond. The 2-butene has just the 1 hydrogen. Those hydrogens are going to shift the most downfield. Everything else, as far as the HNMR, is going to show up in almost an identical space. So it's going to be really difficult to differentiate those. Does that make sense? Okay. Now that we've got kind of a fundamental idea based off our structure, we could scroll down and look at the NMR. And we have the 1-butene and the 2-butene underneath it again. Again, I know it's really, really small, but at least the scales are lined up the same. And hopefully what you'll notice is that in this kind of range down here, those peaks all show up really similar to each other. That's going to be hard to differentiate to identify your compound. However, I get this lone signal chilling out here and this lone signal chilling out here. Those 2 signals are fairly far away from everything else. So if I saw those signals, that would give me information that I had that compound. So we're using NMR differently than we did in our spectroscopy assignment, because in the spectroscopy assignment, you had to determine what your structure was. We're not doing that. You're looking at literature saying that's what the structure is. Does your compound show that signal? Okay? So we could go in and zoom in on what those are. For that 1-butene, the top, we're looking at about 4, let's get color coding right, 4.75. And for the 2-butene, we're looking at 5.2. Almost exactly like the NMR spectra zoom-ins that we saw before. Okay? We decided, or rather I decided for you, that we didn't need to evaluate out there because we're not trying to determine the identity of your product based off a clean spectra. We're just saying, do we see these characteristic signals? Does that make sense? Okay. So, if I have a signal at 5.2, I have 2-butene. If I have a signal at 4.7, I have 1-butene. Make sense? So what could we go back and do? We could look at our NMR spectra. And if you remember, what do we have? I have a signal at that, what did I say, 5.2 and a signal at 4.7. So for this particular experiment, we'll go to the untitled document. Okay. For the base conditions, I had both products. I had both the 1-butene and the 2-butene. For the acid, I have both products. Okay? And we might say, well, if we have both products, neither one was specific for either product. But we can do something else. Okay? Look real carefully at those 2 signals. Do you notice anything different about them? And I know, they're pretty small. Does that help a little bit? What do you notice that's different?
The one at 5.2 is taller on the acid.
If we look at the acid one, the height of our 2 peaks is pretty similar. If we look at the base one, the height is different. What is height tied to? Say again? Integration. And what is integration? It's the amount of hydrogens represented by that signal. Okay? So in this individual mixture, if we assume homogeneity in both the starting sample and here, I could go through and I could compare the amount of that to the amount of that, and I could create a ratio of the 2-butene to the 1-butene. We're already seeing a height difference, which means the ratio of those two, depending on our conditions, is different. Ooh, that's kind of neat. So because our mechanisms ran differently, we might see a difference in the amount of each of those products that came out. And we're doing this based off of the height. Is the height truly what integration is? What is integration? The area under the curve. Which means we got to bust out our calculus skills, and you need to fit this to a calculus curve to tell me the area underneath that curve.
Wasn't a prerequisite.
Is it not? Calculus isn't a prereq for this?
It is calculus.
No, it's not for this class.
Are you sure it's not a prereq?
Yeah.
Oh.
Wait, for this class?
Yeah.
I'm pretty
I
sure
thought
it
it
is.
was for 152.
Yeah, if it's a prereq for 152, it's prereq for this class.
No, I have to retake because mine was more than 10 years ago, so. it was-
Oh, dang. Well, then I guess we need a different way to figure out the area underneath the curve if we can't make you use calculus expressions.
Yeah, the one that you and I fumbled about. What is it? Area of a triangle.
Is it half of it?
This is so stupid. This is calculus.
Yeah.
It's the area underneath the curve.
Yeah.
When they talk about integration, we need the integration, right? The little curvy thing. That's what we're doing. We're just taking infinitely small slices to get the integration. Here, we're just not going to be infinitely small. We're just going to be really big. Okay? So what we need to do is figure out the area of the triangle that represents those individual things. How do we figure out the area of a triangle? Base times height times a half. Where's my ruler? I was waving around all day the other day. Oh, there it is. Okay. So, cool. So I'm going to shout out some numbers. We need some people taking some stuff down. Okay, for our base, 5.2. We're looking at a base, 23. Height, 13.5. And if we were being nice to each other, someone could actually run the calculations and come up with those calculations so that we could summarize them on the board so that you would have this information for a post lab. I think I said 23?
23 times 13.5 and then.
Yes, 23 times 13.5 and then divide by 2. Right. You should take notes on this and then I'll write it up on the screen too for the sake of the recording. You should take notes for this.
She was like, she was too.
Okay, next one. Base 10. 18 and a half. You still have to shout it out, make me feel like I've got to write it down. We got that one? That was all over the base, we good?
It was 10.
Is this on? Did you get the numbers?
I wrote it down.
Okay. We got,
I didn't figure it out yet, I just wrote down the numbers. What
okay, I'm fine with that.
Base is height.
For 4.75, 10 times 18.5, and then divide by 10 again.
Can we do the acid now?
23 times
Maybe it makes us feel better. Oh shit, that's turn the ruler around.
13. So you get when you jump on that one.
Okay, next one. 23. We'll call that one 18. That was pretty close to the same one, isn't it? And then next one. Where's my line? We'll call that 9.5 versus 15.5. Okay, I'm afraid to ask, but we're going to try it. Starting with the base, our red triangle, our area was 155, and it sounds like confirmation in the back. Addison, you got the same thing? Cool. Next one.
92.5.
Oh my gosh, that's stupid.
You're not stupid. Don't stress. You're not the one that used the ruler backwards. Next one.
207.
Last one.
73.62.
Can't read my
Okay.
Yeah, 65.
What's the next thing we need to create?
A ratio.
Yeah, cool. We got that. So 155 divided by 92. And the next one? What was that? I heard 2.8. This isn't 152. We don't need to worry about sig figs. And we probably shouldn't be worrying about sig figs holding a ruler up to our projector screen also, for the record. Okay. So what does this mean? What does that mean?
There's more hydrogen.
The one butane.
The acid one produced more of the signal at the 5.3 than the base one. Right? That's kind of interesting. Right? That might require a different question. Why? Why was one preferenced over the other? To understand that, we would probably have to drill into the individual mechanisms. If it's just about stability, shouldn't both mechanisms produce the most stable product? Yeah, and that's clearly not the case. We're getting a variation here. Okay? And we're actually going to have to leverage a little bit more information into this, which I should have talked about before I started writing, because I'm going to forget. But you already wrote all these numbers down, so you'll be able to tell me. Right?
Yep.
Yeah, okay.
No.
So, despite the no, we're going to move on. But we'll summarize those numbers in a second here. If we take a look, the one but, because I think it's more fun to say that, had our signal show up at 4.7. Right? So the 4.7 was the lower one. That was our one but product.
Who's the one but? Is that two?
You're a one buck.
2-methyl 1-but. What are you looking at?
One buck is 4.75.
1-BUT.
That's a one?
That right there? Yes.
Bro, I didn't blast it.
Oh, we're learning so much today. So we're not going to ask Andrew this next question. So that was our signal at 4.7. What is the number that it shows underneath that? A 2.
That's like bigger.
Okay. Why is that important? What does that 2 represent? 2 hydrogens. So that when we look at the 1 butene product, we had 2 hydrogens there. Ooh, maybe you've already seen or thought of something. If we scroll to the next one, the one that says 2 butene, do you see how the number's different? Just checking. Right. That number, right? Just trying to help out.
Just squint.
This was our signal that showed up about 5.2. And we look at the number written underneath is 1. Wait a second. Can we just take a raw interpretation of the numbers like we just went through and did with our ratios? Sure. The signal that shows up at 5 only represents 1 hydrogen. If this is a mixture, it's going to see 1 hydrogen, which means its height will be half the height. If I had a 50-50 mixture, the signal at 5.2 is going to be half the height of the signal at 4.7. Does that make sense? Because it's representing a different number of hydrogens. We're not trying to create a ratio to look at the different number of hydrogens. We're trying to create a ratio that represents the different amount of molecules present, which means we have to take into consideration the integration within this. Okay? The amount of hydrogens within our individual structure. So what does that mean? Well, what that means is we're now going to zoom out because we don't need to see this quite as carefully. And we're going to try and summarize this a little bit. Okay, so first and foremost, our structure, our 1-butene. Ta-da, 1-butene. Our 2-butene. The 1-butene was looking at 2 hydrogens. The 2-butene is looking at 1 hydrogen. What was the ratio that we saw under acid conditions?
1.67 to 1. Wait, was it bad?
Okay, let's go back to it again. So under acid conditions, what was our ratio? 2.8 to 1. That 2.8 was the signal that showed up where?
Acid.
That was the 5.3, which represented which compound? The signal that showed up at 5.2 was our 2-but. Okay, the 2-but is showing up as half the intensity naturally, which means what do we need to do to account for that? Other way around. Or we could divide the other one by a half. You're right. Okay. I would multiply this one by 2 because I like whole numbers of 1. Okay, which means my true ratio is actually, that's 2.8 times 2. I can't do that. Maybe I can, 4.6? 5.6. See, I was right. I can't do that. 5.6 to 1. What was our ratio for the base?
This one, 1.67.
1.67 of our 2-but. I want to multiply that by 2, and I get 3.3 to 1. So what is that actually showing? The acid is favoring the formation of the 2-butene significantly more than the base conditions. That's what the data shows. Does everybody track how we went through and did that? Okay, and if you didn't, hopefully as we talked through it, it's been recorded somewhat appropriately. Okay, and you can rewatch this section of the video. It's not that there's two possible products, it's the number of hydrogens that represent it. So if I had just a 50-50 mixture, one of the 1-but and one of the 2-but, okay, what would the height of the peaks be? Well, there's only one of each. Shouldn't they be the same height? The 1-but is represented by 2 hydrogens, which means it's going to be twice the height because there's 2 hydrogens representing it. So what we have to do is put it into level playing field by doubling one or halving the other. Either way we do it, we're going to get to the same ratio. I just feel it's easier to double. Does that make sense? We on the same page? Okay. Because what we now move to is kind of sort of a break time, but instead of break time, what we're going to do is divide up the class into 2 categories. One of the categories would be the group of the students that did the acid synthesis. The other side of the group, or groups, will be the base synthesis. Okay? And this isn't you choose which one you do. You've already chosen, it's already been done, you did the experiment. You're going to divide according to how you did the experiment. And what you are going to do is pick a board and draw the mechanism. You can work as a group, right? Just like we've been doing in lecture. Your acid people can all get together and say, this is the mechanism that this reaction must run under. The base people will all get together and decide this is how the base mechanism must run. We'll get those up on the boards to do a couple things. One, get some blood flowing, talk to each other, and have me stop talking for a little bit. And then we can talk through those mechanisms to help explain maybe why we're getting this weird split. Why the acid is favoring the 2-but and the base isn't favoring it as much. So why is the base mechanism running differently than the acid mechanism? Does that make sense? Which I believe is one of the post-lab questions. So we're kind of working through that.